I'm Mike Zajaczkowski, and my topic today is dynamic mechanical analysis, and I will also go into the DMA analysis of adhesives. This is an overview of my talk. I'll start with an introduction which covers the theory of viscoelasticity, dynamic mechanical analysis instrument itself, the information obtained from DMA, and then I'll talk about the dynamic mechanical analysis of adhesives, and then a comparative technique, and I'll finish with a summary. Dynamic mechanical analysis measures the viscoelasticity of a polymer. The basic viscoelastic nature of polymers arises from the fact they are large entangled molecules. And when you apply a force to them, the polymers exhibit an elastic or recoverable deformation due to bond stretching and polymer chain uncoiling. This is known as the storage modulus, or E prime. Polymers also experience a viscous, non-recoverable deformation due to polymer chain slippage and chain scission. This non-recoverable deformation is known as the loss modulus, or E double prime. The elastic deformation can be described mathematically by Hooke's law, and the viscous deformation, or loss modulus, can be described by Newton's law of viscosity. The storage and the loss modulus can be depicted by two models: a spring element for the storage modulus and a dash pot for the viscous non-recoverable modulus, E double prime. The dash pot can be considered a pot with a viscous liquid with a plunger in it. As stress is applied, the plunger resists the stress, but once the stress is removed, it does not recover like the spring element does. The spring and the dash pot can be combined in parallel like this, which describes cross-linked properties, or in series like this, which describes uncross-linked molecular motion. The spring and the dash pots can be combined in what's known as the 4-parameter model, which is the most comprehensive in regards to a viscoelastic material's response to creep. It covers all the molecular motions a polymer system might exhibit. What's depicted here is the stress strain curve predicted by the 4-parameter model. As the stress is applied over time, it engages the different elements of the 4-parameter model. And it should be noted that once the stress is removed, you have a recoverable and a non-recoverable portion. This slide depicts the workings of a dynamic mechanical analyzer. It has a motor which applies a torque to a sample between two parallel plates. As the sample moves under the stress, a displacement sensor measures the strain or rotation. From this information, you can get the moduli information. So a rheometer applies a torque to a sample and then measures the angular displacement and angular velocity. And then the software calculates the stress, the shear strain, and the shear rate. It applies the stress in an oscillatory manner. So when the DMA applies the stress and records the strain, it also records the phase angle, which is the angle between the stress and strain curves. If the phase angle is 0, it's a purely elastic response. If the phase angle is 90 degrees, it's a purely viscous response. But since polymers are viscoelastic materials, the phase angle is between 0 and 90 degrees, and the instrument uses the phase angle to calculate the storage and loss modulus. So what the DMA measures is the storage modulus, G prime, the loss modulus, G double prime, and the tan delta. The tan delta is the ratio of the storage or the ratio of the loss modulus to the storage modulus, and is a good predictor of properties like damping, either sound or vibration damping. Sample preparation. Polymers can be cast in a mold, punched, cut, or molded to form a disc-shaped film. with a uniform thickness between 0.2 millimeters and 1 millimeter, with diameters of 15 millimeters or 40 millimeters, depending on the plate size of the instrument. Instrument software uses the sample dimensions in modulus calculations. Information obtained by DMA characterization include polymer transitions, strength and use temperatures, relative molecular weight information and cross-link density, and the compatibility of polymer blends. If two polymers are mixed, if they display a single TG, they're usually compatible. And it should be noted that you can operate in two modes, a temperature sweep or a strain frequency sweep to obtain this information. But if they're used together, you can generate a master curve to accomplish time temperature superposition, which is used to predict the long-term aging effects of a polymer. So as far as characterization goes in temperature sweep mode, you can see that you can get the melt temperature of a polymer, the modulus of the rubbery plateau, the glass transition temperature, and transitions below the glass transition temperature. Next, we'll discuss the dynamic mechanical analysis of two polyurethane adhesives using temperature sweep. Here's a depiction of polyurethane. They're block copolymers with a highly hydrogen bonded section, and those are dispersed through a more rubbery, softer block. So you'd expect the polyurethanes of this nature to have an extended rubbery plateau, and in fact they do. And that's what you have. You have a long rubbery plateau in the two adhesives. The adhesive 2 has higher modulus and less of a tan delta or less flow or dissipation. So it is higher and stiffer than the lower modulus, more dissipative adhesive, adhesive number 1. So this adhesive would be better suited for bonding stiffer substrates, more rigid things, and the lower modulus, which is more dissipative, would be used for more flexible type substrates. Next, we'll discuss the dynamic mechanical analysis of pressure-sensitive adhesives. Those are adhesives used to manufacture tape. They're usually acrylic, silicone, or polyisobutylene polymers. The pressure-sensitive industry is growing rapidly due to their utility. The Pressure-Sensitive Tape Council establishes tape testing methods, and we'll see shortly how dynamic mechanical analysis can predict the results of those tape methods. So just a brief overview of pressure-sensitive applications. They're used in building and construction, medical markets, wound care and transdermal, automotive, which are higher strength pressure sensitive adhesives, electronics, and they're used in labeling. These are some of the standard tape testing. The first is tack, which is the immediate holding power or how sticky the adhesive feels. Peel adhesion is the resistance of the adhesive to be removed from a surface once it's applied to it. And shear resistance. This is basically the load-bearing ability of the adhesive, or how much weight it can hold for how long. So this is how you perform the testing. You apply the tape with a roller. After a specified time, you peel it in an instron and you measure the force it takes to remove the adhesive from the surface. Again, the bonding is a slow process and the peeling is a fast process. So these types of measurements can be modeled because DMA can take modulus measurements at different frequencies. This is just to highlight the fact that if the adhesive can flow more, it will have excellent wetting or better intimate contact with the surface, which would yield higher peel. Here's a shear measurement. Again, the tape's applied to a panel with a roller, and after a specified time, a weight is hung. So you measure the time of failure. Creep is a slow process relative to peel, the peeling rate, and again, the DMA, since it measures frequencies, can take modulus readings at that creep rate. The tack measurement, basically you take a ball and you roll it down a ramp, and the sooner the ball stops rolling over the adhesive surface, the more tack it is. The rate of this test is between the shear rate and the peel rate. Again, what the DMA will measure on the pressure sensitive is the storage modulus, the loss modulus, and the tan delta. This slide shows how you can use a frequency sweep to predict the performance of a pressure sensitive adhesive. This is known as the viscoelastic windows concept, which was published in the Journal of Adhesion. It has you measuring the modulus at the creep frequency and at the peel frequency. The creep or shear frequency is at 0.01 radians per second, and the peel test is at 100 radians per second. So by measuring the storage and loss modulus at those two frequencies, you can create the viscoelastic window. And based on the moduli at those two frequencies, it places it in a quadrant that predicts adhesive performance. For instance, if a viscoelastic window was created and it resides in this quadrant 2, it would be a high shear PSA. If it resides in this lower quadrant, it would be better for cold temperature, as it would have more flow and able to wet out at cold temperatures. This slide again shows the quadrants that the viscoelastic windows fit into, and you can see that the upper quadrant is for high shear tapes like automotive tapes, and the center region is better for medical tapes. This bottom quadrant 3 is useful for removable adhesives. But you may ask, how can a pressure sensitive adhesive be designed to reside in a specific quadrant? You can design a pressure sensitive adhesive to fit in a certain quadrant by controlling parameters such as the polymer's glass transition temperature, its molecular weight, and molecular weight distribution. You can see that low molecular weight favors wetting, but it hurts creep resistance, and higher molecular weight helps creep resistance, but reduces the ability of the adhesive to wet. So you can see that why it's difficult to design both high peel and high shear resistance into a single polymer, because molecular weight has different effects on tack and shear. A comparative technique to DMA is differential scanning calorimetry, DSC. DSC focuses on heat flow, measures the heat absorbed or released by a sample as temperature changes, allowing thermal events like melting, crystallization, and glass transitions to be measured. It can be highly sensitive to these thermal events, so if you need precise measurements of those, DSC would be the technique of choice. DMA can give you the same information on polymer transitions, but it might be a little bit less sensitive than the DSC. However, the DMA is the technique of choice when you need to obtain viscoelastic properties. So in summary, dynamic mechanical analysis is a versatile tool. It provides information on polymer transitions, measures storage and loss modulus versus temperature or frequency, and predicts polymer properties like stiffness, damping, adhesion, or a range of temperature performance. And also you can perform a viscoelastic windows measurement to predict pressure sensitive adhesive performance. Thank you for your attention.